Hello, this video is going to start the discussion on the various forms of plasma membrane transport. We're going to start off with diffusion, and in other videos we'll cover such things as osmosis, active transport, and then finally membrane potential. Before we can get into the topic of diffusion, we kind of have to look, at least on a basic level, the structure of the plasma membrane. The plasma membrane itself has often been described as a fluid mosaic model, meaning it has a lot of flexibility. It has a lot of give and take. And if you've ever watched a video of a white blood cell engulfing a bacteria, you can see how that membrane has to be very flexible and fluid in order to perform that particular task. The structure of the membrane itself is going to be composed of a number of phospholipid molecules, as seen over on the left. Now, it's the nature of these molecules that lends itself to forming a plasma membrane. We have two distinct portions of that molecule. We have a very large hydrophobic fatty acid region on the lower part of that molecule, and then up at the top we have a very hydrophilic phosphate head. Now, when we put a number of these molecules into a solution, they are going to take on an arrangement that makes both halves of that single molecule happy in its new watery environment. And when we look at the model up top, that's what we tend to see. We tend to see extracellular and intracellular fluid. We see all the phosphate heads arrange themselves to face both the outside of the cellular environment as well as face the internal cellular fluid. The fatty acid portion of those phospholipid molecules will sequester themselves and isolate themselves in their own little hydrophobic environment. So they never have to deal with the watery environments found in either the internal or external cellular fluid. When we look at the different categorizations of these fluids, we obviously have the intracellular fluid, or the cytosol, any fluid that's found inside the plasma membrane. Outside, we have extracellular fluid, which is going to encompass the fluid that we find in the blood, the plasma, as well as the interstitial fluid in between the cells. So when we talk about transport into and out of a cell, what we're really describing is a solute being transported from the intracellular fluid into the interstitial fluid portion of the extracellular fluid, and vice versa. Anything that would cross that plasma membrane into and out of its environment. Also, before we get started on diffusion, we have to generally look at what the differences are between active and passive transport, just to clear up a couple of misconceptions that students have early on. First of all, what drives this transport? And you'll often hear students say, well, active transport requires energy, passive transport does not. And that's not entirely true. And it certainly isn't specific enough for our needs. Active transport requires energy in the form of ATP. We use that ATP to essentially pump solutes across that plasma membrane. Passive transport still requires energy, but in this case, we're going to use energy that's stored in the form of a concentration gradient. A concentration gradient is when we have more solutes on one side of a membrane than the other. We're going to see a driving force pushing those solutes, generally speaking, in a high concentration to a low concentration direction. So they both use energy, it's just a matter of which type. Finally, the end results of each of these types of transports. Because we're using energy in the form of ATP with active transport, we are pumping solutes across. So the end result of an active transport is always going to be the creation of a concentration gradient. We're pumping solutes from one side to the other, and we're concentrating them in that compartment of fluid. Passive transport, on the other hand, essentially works in the opposite direction. They will always go from a high concentration, cross that plasma membrane towards a low concentration side, and the end result is going to be what we call an equilibrium. Diffusion or any other type of passive transport will continue until there's an equal concentration of solutes on one side of the membrane versus the other. There are two different types of diffusion that we'll get into: simple and facilitated. And for the most part, they share a lot of similarities. But there are certain instances where facilitated diffusion will be necessary, and there are other times when simple diffusion is going to be adequate enough or necessary. Passive transport in general is a random movement of solutes. If we simply had a pitcher of Kool-Aid sitting on a countertop, we see a random movement of solutes through that solution continuously. Because we have a concentration gradient where we have an increase in the number of solutes on one side of a membrane than the other, this random movement, just by pure randomness, is going to dictate that we will get more solutes moving across the membrane towards the low concentration side. All of these solute movements are completely random. Just by chance they move more often than not from the high concentration side to the low. Does that mean that the solutes can't move in the opposite direction? Of course not. It's random. But odds are, because we have so many more on one side than the other, we will get a net movement in that one direction from high concentration to low. Going back to our analogy earlier of a pitcher of Kool-Aid, we kind of see what we would have on the left if we simply took a scoop of those colored crystals and dumped it into the pitcher. We would see a very concentrated portion of that water pitcher being deeply colored, and the rest of it probably still very close to near watercolor. If we left that solution to sit, the random movement of those particles would drift throughout that solution until we would eventually get a very even distribution of those colored crystals. So on the left, we have a concentration gradient. We have a high concentration of solute particles in one portion of that pitcher, and they will continue to move around completely randomly until they're evenly spread out in what would be more of an equilibrium distribution. Now, once we go into an equilibrium, does that mean that those particles stop moving? Of course not. They're always going to be in continuous movement. They don't stop moving once they hit equilibrium. So in that case, we have to look at net movement. At what point is diffusion transport, and at what point is it not? In order for it to be considered a form of transport, we have to get a net movement in one direction versus the other. Simply having one enter and one leave is not transport. That's just a simple trade-off, an exchange. So we will see continuous movement, random particles crossing a membrane, and as long as we haven't reached equilibrium yet, we're going to consider the net movement to move in one direction, more so than the other, and even when we hit equilibrium, those solute particles are still moving, but we no longer have a net movement. So if we look at a solution now with a permeable membrane, permeable meaning that the solute can cross. On the left, we have our red particles. On the right-hand side, we have our white particles. We leave these alone, and eventually the reds will generally diffuse to the right until they even out, while at the same time, the white particles will diffuse across that membrane towards the left until they even out. It's important to realize that with diffusion, the movement of the red particles going from left to right does not interfere with the movement of the white particles moving from right to left and vice versa. If we had 100 different types of solutes, each solute will diffuse across that membrane based on their own individual concentration gradients, as if the others weren't present. So we get an independent phenomena of diffusion where all of the different solutes that are undergoing this form of transport doesn't influence the rate or the ability of the other solutes in the environment. Two different types of diffusion that we'll have to deal with: simple versus facilitated. Simple diffusion is when we get a solute go directly through the plasma membrane with no necessary help, directly through those phospholipid heads and through that fatty acid tail environment that we saw sandwiched in the middle of our plasma membrane. Facilitated diffusion, just like the term indicates, requires help. It requires facilitation. So we will use all of our general principles of diffusion when we talk simple diffusion. Some molecules, however, can't undergo simple diffusion. They need a helping hand. So we will employ a transport protein to help these particular solutes get from one side of the membrane to the other. Here's what we look at when we look downward at a plasma membrane. we see our phosphate heads, and we see these spaces in between. Simple diffusion implies that we are going directly through those spaces and crossing that hydrophobic fatty acid environment to get to the other side of the membrane. Facilitated diffusion implies we have these various appearing protein transporters, and you will see them in textbooks in any number of different illustrations. Sometimes they're illustrated as just a simple tube, a tunnel in which those solutes can cross the membrane. Other times we see almost like this Pac-Man looking drawing where we'll open up to one side of the membrane, a solute enters, binds to that transport protein, and then it changes shape and opens up to the opposite side of the membrane. Either way, various different types of transporters, but they're all going to aid solute movement from one side to the other and are going to be part of our facilitated diffusion discussion. When we're trying to determine if a molecule or ion uses facilitated or simple diffusion, it really comes down to two factors. We have to check two particular boxes if we are going to use simple diffusion. The nature of the solute is their size is going to matter, and the solute polarity or its charge. Now, if we don't know what polarity and charge is at this time, I encourage you to go back and watch the video. I will link it below when we look at the atomic structure on ion formation and covalent bonding. That will give you the background you need to determine if a particular solute is a polar molecule or if it's a charged particle. For solute size, there is a general trend, even if we're not talking about membrane transport, between molecular size and weight and how quickly they migrate through a solution. Generally speaking, the larger the solute, the slower it moves. So naturally, if we're trying to transport something across a membrane, slower molecules tend to diffuse across a membrane. There's a general trend when we look at solute movement through a solution, even if we're not talking about cellular transport. And that is the larger the solute, the slower it moves through a solution. So naturally, if we put a membrane in that environment and look at diffusion rate across that membrane, larger solutes diffuse across membranes slower. As far as size is concerned, we are dealing with these small openings between the phosphate heads. So not only do large molecules diffuse through a solution slower in general, but they can't make use of the smaller openings that we see in the middle of those phospholipid molecules. So we're going to require more facilitation to get those large molecules across. Likewise with polarity. Even if a molecule is small enough to fit through those phospholipid heads, doesn't mean they're going to be at home in that thick hydrophobic environment created by the fatty acid tails. So large molecules are not going to be able to fit into the openings, and very charged or polar molecules will get repelled by the internal membrane structure. So if we want to check our boxes again on which solutes can use simple diffusion, number one, they have to be small enough to go through the phosphate openings. And number two, they have to be hydrophobic enough or nonpolar enough to go through that fatty acid environment. If we don't check both of those boxes, then we have to use facilitated diffusion. Other things that can influence diffusion rate. Temperature. If we warm up a solution, particles in that solution are going to move quicker. The distance that needs to be transported. The further the distance that's needed to be transported, the longer it's going to take. Now, with these two variables, they're not going to be considered for our discussion on cellular transport, because body temperature is going to be maintained by your homeostatic mechanisms and maintained at a reasonable level, 98.6 being considered the average. So that's not going to be something that's going to be variable enough to determine rate changes. And in a similar matter, distance transporter. We're always talking about the plasma membrane of a cell. And for most of the cells we're going to discuss, the thickness of the membrane doesn't vary by a great deal. So these won't really be considerations when we talk about diffusion rate into and out of a cell. However, surface area available will make a difference, and the strength of the concentration gradient. Both of those will determine greatly the rate at which a solute moves across the membrane. When we look at surface area available, this isn't always abundantly clear to a student. If we're only looking at simple diffusion, bigger the cell, the more surface area that's available. That's pretty clear cut. When we're talking simple diffusion, remember, we're drifting directly through the plasma membrane. The more membrane we have, more surface area is available. So the general trend we see here is the greater the surface area that's available for transport, the quicker we see that rate. With facilitated diffusion, however, size of the cell doesn't really get involved. It's how many openings we have available to move those solutes across. And in this case, on the left, we have a big cell with 2 facilitated transporters. However, on the right, we have a much smaller cell, but this time with 4 channels. So effectively speaking, the cell on the right has a greater surface area available because there's more openings in that cell for those solutes to drift across. That's only going to apply to facilitated diffusion, however. That's dependent on these transport proteins. Strength of the concentration gradient is going to vary. We will always see a general trend of the stronger the concentration gradient, the faster the rate of transport. And remember, diffusion will continue until we reach equilibrium. So we start with a strong concentration gradient, and we eventually make our way towards a situation where there is no concentration gradient at all, that being equilibrium. So the closer we get to equilibrium, the slower that rate is going to taper off. So we see a trend. Stronger the concentration gradient, the higher the rate of transport. On the left, we see a very strong concentration gradient. 100 milligrams per liter on the outside, 10 milligrams per liter on the inside. On the right, we see something that's much closer to equilibrium, 60-40. The higher the concentration gradient difference, the higher the rate of transport. So on the left, we will see the rate of diffusion of solutes entering that cell to be much higher than what we see on the right. However, there's going to be an asterisk next to that variable. The general trend of the stronger the concentration gradient, the higher the rate of transport, that holds true for simple diffusion. The higher the rate of concentration gradient, the higher the concentration gradient difference, the higher the rate of diffusion. Simple diffusion, right there in a nutshell. However, facilitated diffusion only works under that principle up to a certain degree. And that's because even if in cases we have a very, very strong concentration gradient, the proteins that move those solutes, the facilitated transporters, have a maximum rate in which they can work. So you get a rate-limiting step, not because of the concentration gradient, but because of the actions of the proteins necessary to move those solutes across. So once we see that trend of the stronger the concentration gradient, the higher the rate of transport, once we get to the point where we've saturated those protein transporters, or they're already functioning as quickly as they can work, at that point, a stronger concentration gradient doesn't mean we get a quicker rate of transport. We'll level off and plateau, and that's as fast as we can move things across at that point, in spite of the concentration gradient trying to push it any faster. We call this term a transport maximum. And once you do renal physiology, you will see this work in a practical situation. We filter everything at the glomerulus, and then we reabsorb whatever we should still have in the blood to reestablish normal blood levels. So if your blood sugar is within normal limits, you'll filter that glucose, and you'll reabsorb all of it, resetting and reestablishing normal blood sugar levels. In that case, the transporters involved for moving glucose can operate quick enough to bring back 100% of it. However, if your blood sugar is 3 times normal, these transport membrane, however, if your glucose is twice the normal amount in the blood, these transport proteins can't work fast enough to bring all that glucose back into the blood in the given amount of time that it has. So we reabsorb whatever we can as quick as we can. That just does enough to reset normal blood sugar. The rest of it spills over into the urine. So it's important to realize that these protein transporters have a maximum rate at which we can work. And if the concentration gradient is even stronger, that doesn't mean that they will push those transport maximums any higher than what they already are. So, in summary, we look at simple versus facilitated diffusion. They both require a concentration gradient. That is a principle of passive transport, period. So they're both going to follow that rule. For simple diffusion, there's always going to be a direct relationship between the strength of the concentration gradient and the rate at which those solutes are transported. Higher the concentration gradient, the higher the rate of transport. In facilitated, though, that rate is going to be limited by the protein transporters. So we see the same general trend, but only up to a point, at which point a stronger concentration gradient doesn't mean a faster rate. For simple diffusion, the solutes always have to be small. They have to be small enough to fit between the phospholipid molecules to get into and out of the cell. Large molecules can't fit through those openings, therefore they require larger openings created by these facilitated transporters. And finally, simple diffusion always has to be nonpolar or uncharged solutes. So small molecules like oxygen, carbon dioxide, they're uncharged, they're nonpolar, they get through that membrane with ease because they're small enough to fit and they're at home in that hydrophobic fatty acid environment that we see in the middle of the membrane. For facilitated diffusion, because the molecules that are polar or charged like ions, they can't get through that fatty acid environment. So again, they require a facilitated transporter so they don't have to come in contact with that repulsive environment for them. As stated earlier, the individual solutes involved in diffusion don't influence each other. They will always diffuse across a membrane based on their own independent concentration gradient. And that's important to remember for when we look at osmosis. Again, I will link the video below for osmosis that you'll move on to next. Osmosis works under different principles, and you'll see that when we watch that video. But for diffusion, each behaves as if the others weren't present, regardless of how many solutes we're seeing in a model. So when we look at that, we see potassium high on the inside of the cell, and we see sodium high on the outside. Diffusion stating we'll always get movement of particles from a high concentration to a low. Potassium will diffuse out, sodium will diffuse in. They will do so at the same rate and the same manner as if the other one wasn't present. They don't influence the other. We will see diffusion continue until we reach an equilibrium, at which point the concentrations on either side of that membrane is going to be the same. We use the phrase sometimes an exhaustion of that concentration gradient. At which point we still get movement. Not just movement in the fluids involved, but movement across the membrane. But at that point, there is no net movement in any one direction. So we still get solute movement, we just no longer consider it solute transport. We just get random movement of solutes into the cell at the same rate that those solutes are randomly moving out of the cell. I want to thank you for watching. Again, check out the videos on osmosis, as well as go back and review the material on solutes as far as their covalent bonding for polar, nonpolar, and ion formation. Thank you again.